The next paper's title is Control of Fluidic Artificial Muscles for Rehabilitation Exoskeleton. The authors are Anderson Camp, Edward Chapman, and Paula Jaramillo. And the speaker today is Anderson.
Hey everybody, how are we doing this morning? Good? Great. Alright, so I'm going to talk to you a little bit about control of fluidic artificial muscles for rehabilitation exoskeleton. This is work that's being done as kind of an overarching effort to make an exoskeleton to help patients rehabilitate their hand. So you're probably tired about hearing stroke already, so I'm going to skip a lot of the background on stroke, but one of the main populations that we're targeting is stroke patients or people who have suffered stroke and are in need of some sort of rehabilitation. So the benchmark exercise that we're targeting is called tendon glide. It consists of achieving a variety of hand positions, open hand, straight fist, the hook fist, tabletop, straight fist, and then fully closed fist, and you achieve this a couple times cyclically over the course of maybe 10 or 15 minutes, and maybe do that 4 or 5 times a day. And the point of the exercise is to allow you to improve your hand functionality, prevents tendon adhesion. It can be performed either actively or passively. Actively implies that the patient is providing some of the effort for the activity, and passively implies that the robot is doing all the work. So basically the patient's just sitting here. So we're targeting soft exoskeletons for a couple of reasons that have already been mentioned here today. Firstly, the cost of rigid robotics is higher than that of soft exoskeletons typically. Additionally, we're trying to target an at-home application in the end, and due to the compliant nature of soft robotics, they tend to be safer than rigid robotics as well. Currently, occupational therapists could help you achieve the positions of tendon glide if you were unable to do it yourself, but it's a pretty monotonous and routine task, so really the fidelity of the exercise goes down with time if you have a person helping you, and it's also just not a good use of occupational therapist time. It's a really simple task that's best performed by a robot. So here are a couple of the existing exoskeletons. And the main issue with them, if you want to perform tendon glide, is their ability to actuate joints individually. So shown on the top left there is a glove that's being developed at Harvard. It's pretty advanced, but what it does is it curls or straightens, but doesn't achieve different joint angles individually. So as I showed in the beginning, you need to be able to achieve different hand positions to exercise all the tendons in your hand individually. And current exoskeletons can't really do that. One solution that they've come up with is the actuator shown on the lower left there. They achieve all the different hand positions, but it's one actuator per hand position. And if you'd like to achieve the exercise cyclically, you don't want to have to swap out your actuators every 30 seconds. That would be pretty tedious. So we're targeting an exoskeleton that can achieve all the hand positions for you, kind of an all-in-one package. So to do that, we're going to use fluidic artificial muscles, which are pressure-driven actuators. They were popularized in the 1950s by Joseph McKibben, who's pictured in that photo there with his daughter who had polio. They were originally used on her orthotic device to help remove her hand, or at least that was the highly publicized application in the 1950s. They made Time magazine and everything else. But they're becoming more popular as modeling capabilities improve, and also as people have discovered that they can be used hydraulically just as well or better than they can be used pneumatically due to efficiency and other things that we're not going to go into. But the main mechanism is that with pressure they get shorter. It's an inflatable bladder surrounded by a braided sheath, and that braided sheath translates the radial expansion of the internal bladder into axial contraction, so it just shortens with pressure. Today we're specifically talking about controlling these muscles, and this is the control architecture we use to control these muscles in a hanging situation. So although eventually we'd like to use them in a bending situation across a joint to straighten it, we first look to just simple hanging and contraction. So we supply the desired input signal, and you can see the 3 inputs we use. It's a step, a ramp, and a sine wave. The rise time of the ramp and the sine wave are both 10 seconds for hopefully more analogous comparison between the two. That's fed into an embed microcontroller, equivalent to an Arduino or something similar. That's doing the controls computation. And the output from the control algorithm is a PWM signal, which is sent to the pump, which I'll show you in a minute. That pump causes fluid to flow and causes the FAM or McKibben muscle to contract. And then that's read by a linear potentiometer, which feeds it back into the controller to give you the error. So this is a pump we use. This is kind of one of the unique aspects of the project. Traditionally, as I said, McKibben muscles have been used pneumatically, driven often off of wall pressure, so using servo valves to just flash it with pressure and control it that way. We're looking at using fluid displacement to control the pressure and the position of the muscle. Some other published work we did was a model which relates the the displacement of the muscle to the fluid that you inject into the muscle regardless of load. So just basically a model that allows you to understand the position of the muscle regardless of load by looking at volumetric comparisons. But regardless, this is basically just a positive displacement pump run by a DC motor. That DC motor spins a lead screw, which translates the shuttle, which in turn depresses the plunger of the syringe and causes fluid to flow in either the positive or the negative direction. So it really just simplifies the control architecture because it allows us to control the amount of fluid in the pump simply via PWM signal sent to the DC motor. So the first controller we implemented was a proportional integral controller. Many of you might be familiar with this, but it's basically characterized by two gains, Kp and Ki, which are scaled by the error and the integral of the error, and then the sum of those two terms is your control effort, which, as I said, in this case is a PWM signal. So this is the results for the PI controller and the hanging test for a step input and a ramp input. You can see that both ultimately achieve the desired endpoint, which in this case was 20% contraction or 0.2 strain. You can see some lag in the ramp signal from the PI, and we'll see that later. We're going to discuss both sine waves later. But for here, you can see a lag of about 0.8 seconds. You can also see the simulated response agrees pretty well with the experimental response. But ultimately, the PI controller was capable of achieving really what we wanted it to do was a change in contraction of 20%. So that controller we applied was the model reference adaptive controller. In contrast to the PI controller, this controller is characterized by gains that change with time, hence the name adaptive. So here, rather than tuning the actual gains themselves, we're tuning the rate of change of the gains, as well as the other main difference between this and the PI controller is that rather than compared to just the desired input, it's compared to a reference system, a first order reference system, which is achieving that input. So there's a couple things we can tune here, 6 in total. The parameters of the reference system, the rate of change of the gains, and then the initial condition of those gains, we can give the controller basically a head start to reduce oscillation a little bit. So that's the main difference between the two, and I'll show you some results from applying the model reference adaptive controller. So here you see the results for the step and the ramp again. You can see that it's not what you would expect for a ramp. A step, it's a first order reference system responding to a step input, so that's the comparison that's happening now. You can see some initial oscillation for them in the step, and smaller but also initial oscillation in the ramp. That's fairly typical of model reference adaptive controllers. It can be tuned down, and this was about as good as we could get it through tuning. You'll note that it's not shown in the model, but it is shown in the experimental results, so there's some discrepancy there. But basically what we've eliminated here with the model reference adaptive controller is the lag that we saw in the PI controller at the cost of those initial oscillations. So the sine wave is really what we were targeting because that replicates best how you perform tendon glide exercises with these muscles. It's slow, it's cyclical, and it's repeated. So you can see here that the PI controller achieved the shape of the sine wave with that same lag that we saw for the ramp input. And you see the model reference adaptive controller eliminates the lag, but at the cost of some oscillation. Across the board, because it eliminated that lag, the average error of the model reference adaptive controller was less. But really the results of this was that both of these controllers had their advantages, and when we go to implement these controllers in hardware, depending on the application or what we see as far as clinical results go, one may be favored to the other if we'd like to eliminate the lag, or this overshoot is a complete non-starter, would eliminate the use of the model reference adaptive controller. But the other aspect of this project is the hardware, so I'm just going to touch on it briefly. If you can't tell by the freckles, it's my hand there being compared to the test finger. So that test finger was constructed to allow us to test the performance of the theorized exoskeleton without obviously involving a human hand. You can see here there's 2 FAMs laid across the 2 distal joints and 1 FAM laid across the joint approximate to the palm. As they contract, they control the angles of those joints, and then a restoring force pulls it back to the curled position as the resting position, and the flex sensors measure the angles of the joints. So using human-in-the-loop control, this is a 4x video, but we were able to achieve all the different positions that we wanted to do. So first you'll see, if it is playing, Well, I have pictures, just in case. So you can see all the different positions we were able to achieve. Starting with the open hand, then going to the hook fist, tabletop position, straight fist, and ultimately back to curled, and these positions could be achieved cyclically. So this, from a hardware perspective, was basically proof of concept for us. But the next step, before we go into implementing the controllers in this application, we wanted to make a test bed that would allow us to test both the wearable exoskeleton on a person versus without having a person in the equation. So we made the wearable exoskeleton, which is really just made up of three main pieces. It's a fingertip cap, a ring, and then a base, which attached to a wrist splint that you can put on the hand, and then a test palm and test finger. So we were able to eliminate the person from that equation. But as you can see, it's still wearable for a person. So this is the test bed we're going to use moving forward in implementing those controllers that we tested in the linear situation. And we're also working to improve the range of motion. We did do some initial control implementation for this setup here, but we found that the sensors were giving us too much noise in this situation. The setup, they're flex sensors, so they're resistive flex sensors, so they're pretty sensitive to movements and the anchoring point. So in this configuration, they're anchored much more firmly, which we hope will give us a better sensing signal, which will allow us to implement controls a little bit more robustly. So that's the next steps here, is implementing controls for this device and achieving the full range of motion for the task that we'd like to achieve. So this would be playing as I took any questions you might have, but we're not working on the video. Sure.
Thank you. Thank you, speaker. Nice work. Any questions?
Okay, so how important are the thumb movements for this exercise, and are you planning on assisting with that?
Sure, so the end goal, of course, when you start with one finger, you want to go to all five. Thumb, from this perspective, obviously vital for grasping and everything else. It's less involved in the normal programs that you see for tendon glide as a specific exercise. Tendon glide is kind of a catch-all term. There's many exercises that clinicians call tendon glide. Some of them involve the thumb, some of them do not. But obviously, we would like to also rehabilitate the thumb, as that's one of your more vital fingers you've got going for you. So yeah, eventually we'd like to expand to all the fingers. But this is just kind of a test. I mean, the issue becomes scale. These muscles, you can get about 25% contraction out of them. So to go from the fully curled to the fully extended position might be more difficult on the smaller fingers, but we're starting with the index and hoping it scales. So, thanks for the question.
I guess I just wanted to ask you, how did you get your model for the...
Sure, yeah, so that's a whole nother talk.
yeah, just like roughly.
Yeah, so it's...
What was the order, by the way? What was your order?
Of the model, so it's actually all geometric, so there's no dynamics or anything like that. So it just looks at the change in volume of the syringe pump to the change in volume of the muscle. So it's based purely on those braid angles that work. So we didn't really touch on order or anything like that, just because... What's that? No transfer functions or anything like that, no dynamics, so we tested it quasi-statically and found that it scaled to dynamics with some adjustment, basically. Some constant adjustment worked pretty well for it. So if you want, that's in the International Journal of Robotics Research we published, so you can read about it.
We have time for two more quick.
Why do you think there was a lag in the PI?
Just because that's how PIs work. I mean, they're kind of working reactively. Like the integrator builds up with time to get it to converge to the steady state. So if you're constantly changing what you'd like it to get to, it doesn't have time to adjust the right way. So you see there's no lag. Where's the step? There's no lag for the step because the whole point of the integral is to get convergence, but as you're constantly changing that, the integrator doesn't have time to catch up, I guess you would say.
I have two questions. So,
sure.
There's a lag in the PI controller. Do you think any feed-forward gain could have combated that issue? Did you try something with the feed-forward gain?
No, we didn't try any feed-forward, and I'm sure there are other parameters we could introduce to this PI to help combat that lag. We're actually looking at, it's a PI adaptive controller. It's a combination of an adaptive controller and a PI controller, which eliminates the lag and basically combines the benefits of both. So we are, of course, looking at implementing controllers that combine the good features of both of them.
Another thing is, were you able to calculate the stability margins in the bandwidth? And when it comes to exoskeletons like this, what is the expected bandwidth of the system?
So really low. I mean, for the application we're targeting, we're looking for slow cyclical exercises. So I mean, like 30 seconds for full contraction and then holding and then relaxing. So we didn't really try and figure out how much bandwidth it could handle because we didn't need to worry about that so much. We knew we were targeting slow exercises. Sure, of course.
When the the tubes expanded, how did you ensure that it went straight and not sideways?
Sure, so that's in the test finger that we used, that was easy because they were basically. Oh, that's mine. Yeah, I don't know if it'll be able to come to you because it's for a surface.
See if you have something to.
The HDMI.
Here's, yeah.
Oh, sorry.
Yeah, they're basically, for the test finger you saw, the one that achieves that position is basically welded on there so there's no rotation happening. For the ring, you basically just go for a tightness of a fit. And for the fingertip, to make sure it's not rotating off to the side, it's elliptically shaped rather than circular, so you're basically just taking advantage of the geometry of the finger to ensure that it's not rotating off to the side.
Thank you very much. Nice talk.